Sorry, does the share preloaded slides option work?
Okay, let me try that again this time. Okay, can everybody remote and in the room hear me now? Yay, okay, whoop. Okay, so welcome to the PEARG meeting at IETF113. This is a hybrid meeting. You will have noticed that unfortunately none of the chairs are able to be there in person. So there is a sad little empty desk at the front. I will remind everybody that this meeting is being recorded before we go any further. And if I can ask for a volunteer for a minute taker, if you're interested in that, please contact the chairs via the chat. Okay. As usual, we have the Note 12, which we hope that everybody is familiar with and has read. And in particular, we draw your attention to the Code of Conduct, the highlights on this slide, and we expect everybody to adhere to that. Moving on to the agenda. The blue sheets are generated automatically by your attendants in Meet Echo these days. Shivan will be acting as JavaScribe. He'll be monitoring the chat, so if there's anything you want to put in there you would like asked at the mic, please prepend it with Mike and he'll bring that to the queue. We have a note taker, thank you very much. And our agenda today is fairly light. We have one presentation on the effectiveness of quick padding against website fingerprinting. We have a presentation on GDPR and network privacy. And then we have one update on the state of the Servo Worldwide Censorship Technique draft by Mallory. Before we get going, I will just quickly ask or remind people that participants in the room will need to join the queue via Meet Echo, and then they can go up to the mic to ask the question. But when they do, please do state your name clearly, as with masks it makes it particularly hard to see who is speaking. And if all participants can keep their audio and video muted when they're not speaking, that will be much appreciated. I see that there is an echo. I hope that's not me. I will switch to a headset. Okay. So some folks are hearing it and some aren't. So I don't know if it's... Okay, maybe the in-room mic. Yeah, maybe the in-room mic is picking something up. Hopefully that will get sorted out. We will start by moving on to the first presentation given by Sandra Sibby. Sandra, would you like to request to share your screen, drive your own slides?
Hi, can you hear me?
Yes, yeah. Let me stop sharing. You go ahead and make a request.
Let me try to share my slides.
Yes, if not, we think we can try. Okay, that looks good. I can see your slides. Please go ahead.
Let me just try to move the slides. Okay, that works. Sorry for the echo. Okay, hello everyone. Today I'm going to talk about our work on developing defenses against website fingerprinting of quick traffic. This is joint work with Ludovic, Christopher, Marwan, Nick, and Carmela, and we are from EPFL and Cloudflare. So before I go into the details of our work, I just want to give a quick overview on website fingerprinting. So let's say that we have a client, and this client is trying to visit a web page, in this case, example.com. We have an adversary that's on the path between the client and the destination host. And the adversary is observing the traffic between the two parties. Now, since the channel is encrypted, the adversary does not know which web page is being visited by the client. All the adversary can see is some metadata of the traffic. And in this scenario, the IP addresses. We assume that there are measures such as ECH or encrypted DNS so that the adversary does not see the domain that the client is visiting. So the goal of the adversary in website fingerprinting is to determine which web page is being visited from just observing this metadata. In order to do this, the adversary has a pre-trained machine learning classifier that's already been trained on some network traffic traces that they've collected. So what happens here is that the adversary gets the traffic sample and then creates some features. So on the left side of the slide, I have some of the characteristics that the adversary uses in order to develop these features. And these features are then fed into the classifier. And the classifier spits out a prediction on what web page this could be. And this is how the attack works. So in our scenario, we are interested in seeing how website fingerprinting works over a quick connection between the client and the destination. Now, website fingerprinting on quick traffic is not new. It's actually already been done, and this work was actually presented at the IETF last year. And they concluded that it is no harder to fingerprint quick traffic as compared to TCP, and the adversary can identify pages over a quick connection with high accuracy. What we are interested in looking at is whether it is possible to develop defenses against being fingerprinted by such an adversary. So if we look at the quick RFC, there is this option for a quick padding frame that allows you to increase the size of quick packets. And the RFC specifies that this padding could potentially be used to provide protection against traffic analysis. And this is what we are interested in exploring further. So I want to talk a little bit now about the adversarial model that we are considering. So we have a bunch of vantage points, which can be routers or switches or middle boxes on the internet, and they're located in different ASs. So let's say that we have a client in ASX in this scenario, and the client is interested in visiting some web pages which are hosted on destination hosts in another AS. This is for simplification that they're all in the same AS, but they could be located in different destination hosts in different ASs. Now, these web pages can host sub-resources, which are also located in many different endpoints. So when the client tries to visit and obtain these resources, the network traffic passes through a bunch of different vantage points, as seen by the red arrows here. So in our scenario, the adversary is an AS that is interested in finding out which web page is being visited by the client. Now, these vantage points will collect different subsets of the traffic. And as we saw here, we have a machine learning classifier, which which requires collection as well as storage and computation on these traffic traces. So because of this, we actually have a centralized location in each AS, and all the vantage points transmit the traffic that they collect to this location, which actually performs the website fingerprinting attack as seen by the purple arrows. So what we want to do now is the goal of the adversary here is to identify the correct web page among all the web pages that are hosted on a single IP. So since the IPs are seen by the adversary, they can already filter traffic based on IP address. So they just need to identify which web page is being visited among all the web pages that are hosted on one IP address in our scenario. So we do our experiments with a quick dominant data set of 150 pages here. So we did this by crawling the web pages in popular lists such as the Alexa 1 million. This is similar to prior work that's been done on quick traffic. And we looked at which web pages have a high proportion of quick traffic. Since Quick is still being adopted, a lot of web pages are still transmitting their resources over non-Quick connections. But since we are analyzing Quick, we wanted to build something which has primarily Quick traffic. And we found that for our data set, we had approximately 70% Quick traffic on average. Just want to note that previously we tried to be more realistic and we partnered with Cloudflare to look at domains that are hosted on a single IP and get the traffic for those, but those had only about 4% quick on average. So we went with this method to build our data set. As I mentioned, this is the process that we have for the website fingerprinting. But now we see here in the second step, we apply a defense to the traffic sample, which I'll come to in the upcoming slides. And then we pass this defended sample into the classifier. And we see how well the classifier performs against these defended traces. We are using a couple of well-known classifiers from the literature, which is there in the yellow box below. If you have any questions, you can ask me about that later. So the metric that we are using to evaluate is a common metric used in these kind of works, which is called F-score. Now, F-score is the harmonic mean of the recall and the precision of the classifier. So recall means how many relevant results are returned by a classifier, and precision indicates how many of those are actually correct. So we have 150 pages in the data set, which means that if we were to have an adversary randomly guess which web page it was, we would have a 0.67% chance of getting this right. But we see actually that for our classifier, we get a 96% F score, which means that on undefended traffic, the adversary has a very good chance of identifying the web page that is being visited by the client. So when we look at what features are important for the classifier, we see actually that the size-based features are very important. So how many packets of particular sizes, as well as the total number of bytes that are incoming and outgoing, are mainly used by the classifier to identify the page. So the first thing that we do is we try to apply some defenses to hide these features from the classifier. So the first thing that we do is we pad individual packets and hide the packet-based features as shown in the figure here. And we see that that does not really decrease the F-score by a lot. It goes down by about 2%. The next thing that we do is we hide the total amount of traffic in both directions by applying some amount of padding to each of the packets. And we still see that the F score is really high, which is about 92%. And now we look again at the features of the classifier to see why it is doing so well when size-based features are no longer used. And we see that there is a lot of directionality-based features that are still leveraged by the classifier. So hiding the total size and individual size does not hide how many packets are going in each direction. And this is now being used instead of the size-based features. So in order to hide the directionality-based features, we now perform this defense where we inject dummies randomly into the trace. And what we actually see is that injecting dummies does decrease the performance of the classifier, but it also comes with a high cost. So we see that it goes down to about it goes down by about 16% in the worst case, but with 100% overhead when you add these dummies. And this is not including the additional traffic that is injected in order to hide the packet-based features. So what we conclude is that these network defenses offer low protection with high costs. For example, just to get a 10% reduction in F score, we need more than 50% overhead when it comes to dummy injections. Now, so far I've talked about an unconstrained adversary, and this adversary observes all the traffic and also performs this classification with all the traffic that it sees. But in reality, it is possible that you don't have a perfect adversary, and adversaries can be constrained not just in the amount of traffic they see, but also in what they do with this traffic. So the first thing we look at is an adversary that has a limited view of the traffic. So for example, if you have a vantage point in AS5, you might miss a lot of the other red arrows and the other traffic that the client is generating. So in order to see what ASs actually observe how much of the traffic, we generated trace routes from the client for all the pages in our data set and observed how these trace routes vary. So this is the result from one of the vantage points that we conducted the experiment from. We did this on multiple vantage points and we observed similar trends. And what we see is that there are only a few large ASs that can observe a large proportion of the traffic in the first place. So that means that here in this scenario, on the left plot, we see that there are only three ASs that can even observe more than 50% of the pages in our data set. And on the right plot, we see that for those pages, only about three of them can observe more than 50% of all the routes for each page. So this means that a lot of the adversaries, just by virtue of their location, might not even be able to successfully conduct an attack. Another interesting thing that we saw was that Google actually has a large prevalence on the pages. So more than 80% of the pages on our data set contain at least one resource that is hosted by Google. And found that actually these resources could be ordered differently on different web pages, which means that timing to Google resources is a low cost fingerprint and can have up to 77.9% F score. This means an adversary, for example, like an ISP, can just use timings to Google instead of using all the traffic that we observe and identify things with high accuracy. The next thing that we wanted to see was how well these adversaries perform with limited processing. So previously, I said that the vantage points are transmitting all the traffic that they observe to the centralized locations. Now what we wanted to see if instead of transmitting all the traffic, whether these vantage points can just transmit flow summaries of this traffic to the centralized locations. So in order to simulate this, we used something called sampled net flow. So what happens here is that the packet traces are sampled, and then flow summaries are created, and these are sent to the centralized location. And we perform the attacks with the summaries instead of the packet traces. And we experimented with various sampling rates to see what happens to the adversary's performance. So, as expected, we see that with lower sampling rates, you also have much lower performance of the adversary because there is much less traffic for the adversary to make good features from. Just want to note that even at a 0.1% sampling rate, it is still much higher than the random baseline. Then, when we apply the padding-based defenses, we do see that there is some reduction in the performance of the adversary. However, we want to point out that in the case of the limited adversary, a lot of the gains come from the sampling process here more than the actual application of the defense. So what we actually find is that the network layer defenses in the case of both unconstrained and constrained adversaries do not efficiently hide a lot of the global features. And the main reason for this is that they do not know the sizes of traces in advance to efficiently design padding strategies. So there is no application layer information that is given here, and so you need to randomly inject dummies or add size-based defenses, and this can really increase the overhead on these network layer defenses. So then we wanted to see whether applying defenses at the application layer could potentially help protect against these attacks. So in order to do this, we started analyzing the structure of web pages. So here's a quick refresher on terminology that I'm going to use. So let's say that we are visiting a page example.com. You might have resources from the same domain, example.com, and these are called first-party resources. Or you might have resources from other domains. So here you have tracker.com, and these are called third-party resources. And when we look at the web page structure, what we see is that in our data set, 18% of the web pages actually have a very small number of first-party resources. So you actually have a large prevalence of third parties. And there is indeed a large prevalence of Google resources in our data set. So 24% of the pages actually even have more than 50% of Google resources. So what does that mean when it comes to applying a defense? It means that the third parties are contributing a large proportion of resources to the web page, and in order to apply a defense, we actually would need cooperation from all the parties that are supplying some resource to the web page. And we actually did do experiments on this where we hid the resources from third parties or from first parties to simulate the scenario of only one of these parties participating in the resources. And then we went for the application layer defenses. So we applied the same packet and trace-based padding but at the application layer. So we are protecting the actual resources here. And we still see that the padding is ineffective here once again because the adversary just uses the ordering-based resources. However, when we apply dummies now into the resources, we actually see that this can be more effective than in the network layer case. And for example, injecting 5 dummies on average reduce the F-score by 39% with a relatively low cost. But in reality, if you wanted to implement something like this, that actually comes with some deployment complexity because injecting dummies here means that you're actually sending some requests for some dummy resources. And we'll have to think about how those would be implemented uh, and how that would impact the client's experience. So in short, what we found is that at least at the network layer, if we want to implement an efficient resource, we need some sort of information from the application layer. Otherwise, this could lead to large overheads. At the same time, if we decide to implement things on the application layer, they come with a whole set of other complexities. So they would require some sort of coordination between parties, or we would have to talk to developers on how to write code so that resources are always fetched in some sort of a standardized manner. And finally, all of these changes in the application layer could potentially have a large impact on client experience. At the moment, we are working to see further what kind of practices would have to be done in order to develop better application layer defenses. And here's a link to our paper, and feel free to ask me some questions. Thank you. I see some people in the queue. Sharon?
Yes, hi. How are you, Sandra? Thank you.
Hi.
I have a question for you.
Yep.
If you think of the definitions slightly different, where the adversary is actually the client sending traffic because he's malware and he's doing some data leak or lateral movement, and the one sampling is the protection software that
Mm-hmm.
that really has a very high score by sampling NetFlow and detect the rogue client. So according to your analysis, the only way the malware can throw off the detection sampler is by injecting a lot of dummy traffic into whatever it does to avoid the pattern recognition. Is that correct?
Uh, so you're assuming here that the client is the adversary, right?
Yeah, he's malware. And I want to detect him by sampling. And you're saying if I use Quick, it's not going to reduce my F score. But
Mm-hmm.
if he's going to use a lot of dummy traffic in his malware, then
Mm-hmm.
then yes, but at a high
Mm-hmm.
cost. Something like that?
Yeah, so in this scenario, what you're saying is that actually analyzing the network traffic would be a
A
good
good
thing
thing.
because you want to detect
Yeah.
the malware.
Yeah.
Yes.
Yes.
I
Yes.
mean, what I'm saying right now is that generally most of the defenses that we have, or rather in this scenario, anything to prevent this detection, are not going to help much. So you would be able to detect this with a large accuracy already. And if the client wanted to protect against that, they would have to think of some good way of injecting dummies, as you say.
Great. Great. Thank you very much. We'll look forward to seeing some raw data if it's possible to share.
Yeah, we'll be sharing that.
Thank you very much.
Thanks.
Nick,
Um,
did you want to go next?
Yeah, thank you for this presentation. It's very useful for us to think about this type of threat, and it's useful to get some data. I'm curious about clarifying the threat a little bit more precisely. I've just
mhm.
skimmed the paper, but my understanding is that you removed all caches and just made a single web page load to the index page of each popular domain name. And the goal was just, can you distinguish loading the index page with no caching of one domain versus another in cases where, for example, they're hosted by the same CDN or something like that?
Yes, that's right.
And so I'm just curious, like, how is this type of attack going to apply to cases where maybe I don't go to the index page, or maybe I load a customized resource, or maybe I have cached resources, or various other situations like that. But because it seems like many of the times that we're worried about the network adversary, we're worried about them learning what I'm reading, or the contents of my messages, or lots of different threats. And that's not to downplay the threat of them knowing that I'm even going to a particular domain name, but does this threat also apply to learning what pages I'm visiting, or cases where the network traffic is going to be mixed, or resources will be cached, etc.?
Yeah, that's a good question. And this is also a field of research in this area. So, like you said, we are working with relatively clean traces here, where we are assuming no caching and like no background traffic, and it's just the home pages. But we are planning now, for example, to do some experiments where we are also visiting sub pages of different websites to see how well this attack is going to work. And there is also, I think, work done by others now. There are some papers coming up where they're looking at fingerprinting in the presence of all these factors that add some noise. But yeah, I would say that this is kind of the worst case for the worst case. I mean, the best case for the adversary, and all of these factors would possibly lead to a reduction in the F score. Does that
Okay,
answer your
but we don't
question?
know how much of a reduction, but yes, it will be worth
Yeah.
further research.
Yeah, we'll probably get some numbers when we run this, possibly next month.
Okay, great. Well, I think many of us will be interested in those numbers too. Thank you.
Thanks.
Okay. Sandra, thank you very much for that presentation and for all the questions. There is some interesting discussion in the chat, and I'm sure Sandra will follow up there on that as well.
All right. Thanks, Sarah.
Yeah, thank you. Okay, so our next presentation, I believe, is one by somebody in the room, a real person. There we go. Step forward. Thank you.
Yes, that's me.
Okay, so do you want to attempt to share your screen? Okay. Sandra, you may need to stop sharing your screen, please. Okay, great. And okay, here come the slides, I think. Okay, I think they've loaded. Okay, go ahead then, please.
So I'm Luigi. I'm going to present a little bit the relation between GDPR.
Okay, Luigi, I'm having trouble hearing you. I don't know if everybody else is as well. Maybe you're okay in the room, but it's quite quiet remotely.
Hello, better?
Better, thank you.
Okay, just to hit the mic with a mask. Okay, I'm going to talk a little bit about GDPR in relation with IP addresses in general, a little bit. As the title say, how layer 8 meets layer 3. Okay, knowing I'm not a lawyer, just to be clear. So this is my interpretation. I spent some time reading it, and so I'll give you some interesting point that we may discuss later on. So I'll really, one slide history, some terminology, and then we dig a little bit in GDPR and IP addresses. There is a few slides that make a clear link between existing RFCs and GDPR. If time, we will go over that as well. Okay. So GDPR came into effect in 2018, so it's not that long ago. Replaced a very old Data Protection Act in Europe. It is a regulation, which means it is slightly more complex than a simple law, because there are articles, which are the law itself, but there are also recitals, which are notes that explain actually how to apply the laws, okay, which is the body of GDPR.
Luigi, I think it's still pretty quiet. If you wouldn't mind just, I guess, speaking up, I guess, a little bit.
Speaking even more up. Okay,
Yes,
I will
please.
try to do
Thank
that
you.
as much as I can. Okay.
Thank you.
The key point is personal data. Okay, what is personal data is anything that can identify a natural person. Not a legal person like a company is different. A natural person like me, all of you in the room and connected elsewhere. Name, personal addresses, anything that can identify ourselves. Information concerning our employment. Financial information, you have the details in this slide, which is pretty wordy. There are also sensitive information, which is like ethnic origins or religious belief or anything. It's real personal choices in a certain way. And any other information that actually you are willing to disclose by yourself, for example, to your employer. Okay, in this last bullet, I put my employer, but it's just any employer can, or any entity can ask you for some information that you may wish to disclose, but is really personal. This is about the personal data. Then we have three key points, which are controller, processor, and processing. So the controller is who is controlling the personal data, okay? Because if you give the data to someone, that someone is controlling your personal data, okay? And he may wish to do some processing, which is the action of taking your data and making something to get some stats, for example, right? This is the processing. And the entity that does the processing is the processors, okay? Which is actually doing the processing. Now, it's kind of a headache, but these three things are correlated and do overlap, okay? It's like I connected to my ISP, assign a contract, I give some personal information, the ISP controls my personal data that I gave to him, okay? And he may decide to do some stats, okay? And he decides how to process the data, but not necessarily does it itself. He can ask somebody else, a third party, to do it, which will be the processor, okay? Now, GDPR and IP addresses. So in the GDPR, is clearly stated that any online identifier is personal data, okay? Especially this applies to IP addresses, and the European Court of Justice ruled that it is personal identification data because you can associate and retrieve a lot of other information, even if you use temporary addresses, okay? So as such, it falls specifically under GDPR and privacy protection. Now, I will go a little bit through the several principles of GDPR and try to make a link to what is an example of how does it apply on the protocol stack, let's say, and more specifically to the network layer, okay, and IP addresses. The first very simple principle is lawfulness, fairness, and transparency, which basically says that if I give my personal data to my ISP, I expect that it does use my personal data according to the law. GDPR is part of it, okay? In a non-discriminatory manner, okay, and in a transparent manner, which includes my explicit consent. I will come back to this a little bit later. Second principle is purpose limitation, is the fact that my ISP is not allowed to use my personal data for whatever he wants, okay? He is able to use my IP address in order to count my packets for billing purposes. He's not allowed to look what is in my packets in order to measure how much shopping I do online, because this is not related to the service that it proposes. The ISP is proposing internet connectivity, okay? Third principle, data minimization, is the fact that my ISP is allowed to collect as much data that is needed to offer the service, but not more of that, okay? So he can certainly, again, access to the IP header, the transport header to provide the service, but not access the content of my packet in order to look at what I actually do exactly, even if it isn't clear, okay? Accuracy, fourth principle, is the fact that anything the ISP gathers of me must be accurate, okay? Or error-free, if you wish, okay? Storage limitation is the fact that my data cannot be archived forever, okay? There is typically a limited amount of time that my data can be collected, then it should be deleted. If I do not ask actually to do it beforehand, because there is also this aspect that actually I have the right to be forgotten, so that I can ask to delete all my data, okay? This is interesting, is kind of a tussle in somehow, because on the one side we have GDPR that asks storage limitation. On the other side, law enforcement enforce some minimal time to keep some logs for accountability and traceability of some stuff. So there is a balance to strike there at some point, okay? Security, integrity, and confidentiality is just that if I give my personal data to the ISP, I assume that the ISP is doing his best to protect my personal data and they do not go out in the wild, okay? Which brings to the fact that he is actually accountable for my personal data. And even in the case, as I explained before, that my ISP is the controller of my data, and it gives my data to someone else in order to process them, okay, to perform a processing. And if something goes wrong and the processor actually leaks my data, the one that is accountable from my perspective is the ISP, okay? It's not moving anymore. I don't know why. Okay. So this is really high level what happens in GDPR and how we can relate with the IP protocol stack. So it's known that GDPR is peculiar for the European Union. It's not the only example, okay? In this table, there is a summary of other laws and regulations you can find all over the world, okay? There are more or less or similar, and they all more or less consider IP addresses as a personal data. There are some legal nuances in a certain way. So, for example, in Brazil, it is not explicitly stated that IP addresses or online identifiers are included in the law, but the way the law is expressed, IP addresses fall in, okay? Another interesting peculiarity is the fact that in Japan, even anonymized data are covered by the APPI, which is the Japanese equivalent of GDPR, which is not the case here for GDPR in Europe. Once you anonymize the data and you are sure that there is no way to go back and find the original information, GDPR is out of the scope, okay? And all of the laws are based on consent, usually explicit consent, which means that you have to take an explicit action to give your consent, which means when you are in Europe, you have this pop-up window that says you accept the cookies and you have to click yes or no. And today we have also different settings. This is a explicit action, okay? You cannot just put someplace in the web page, oh, by the way, we are collecting cookies. If you have something against, please shut up, speak up, okay? So you cannot do that because it would be a passive consent, okay? And in Canada, on the contrary, this is allowed, okay? We have...
Luigi, you have about
Yes,
3
please.
minutes left. Thank you. If
I would like just to make one single point. You can go over the slide. There are the RFC numbers, which try to make a clear link between GDPR and what we do here in the IETF. The only thing is this slide in RFC 6973, there are already some wording that clearly points to the same principles that we can find in GDPR. So just to state, it's not out in the moon. GDPR is something that in a certain way we already share as a principle, okay? And I think I'm done so that we are in time.
perfect. Thank you so much. And thank you for giving this talk on a topic which comes up repeatedly inside the IETF. I see we have Patrick in the queue. Please go ahead, Patrick.
Hello, Patrick Tarpey. Very interesting presentation. Just an observation, really. It's a kind of known fact that in the European Union area, there's a piece of regulation called the Data Retention Directive, which requires communication providers to keep call data records for the purposes of lawful intercept and all that malarkey. To what extent do you think that new protocols such as MASC over QUIC and oblivious technology, to some extent, render this conversation about the privacy of IP addresses, or indeed, you know, the actors that you've mentioned in your presentation, kind of obsolete, really? Do you think that's a fair comment? You know, the evolution of MASC, proxies, and oblivious kind of make this idea a bit less fungible and a challenge.
Thank you for the question, actually. It's a very, very interesting question. Top of my head, the answer is, I think these technology are very useful and can help in privacy protection. There is one thing, though, that should be considered is where the data goes. Because the fact that you have an oblivious methodology in order to obfuscate some things doesn't mean that you are GDPR compliant, because you have also to consider where actually you do that, how you do that, and then come into play the logs that you keep in order for accountability. So does it make sense, my answer? But we can chat more. It's a very interesting question, but it's very complex, I think, to discuss.
Okay.
Okay.
Thank you again, Luigi, for that presentation. That's great. And again, there's some further discussion in the chat that you may want to follow up with.
Yeah, sure. Thank you.
Thanks very much. Okay, and our final presentation is from Mallory on, it's an update of the Survey of Worldwide Censorship Techniques draft. So please, do you have slides? Do you want to share your own screen?
I do have slides. I just requested to share them.
Yeah, there we go. I see it now.
Thank you so much.
Yeah, go ahead.
All right. Thanks. And thanks for your time on the agenda. This is a research group document, if people recall. I'm presenting it only because the other authors who've worked on this draft for a very long time no longer have the capacity to continue working on it. So a lot of the content in the slides and the draft itself is not written by me, but I am its steward at the moment, happily. So yeah, Joe Hall, he was originally in my position at CDC when he started writing this in November 2014. So that's quite some time. I think one of the challenges of this draft is that, of course, it's a, contentious topic, uses the word censorship throughout. It's not something that IETF is used to talking about, but also that the more time that passes, the more sort of techniques can be added, refined, So at some point, I think there's a recognition. This has been made, this has been recognized multiple times in PEARG that it just has to sort of be published. So we're working towards a document that is good enough to be published, but also, has sort of timestamp on it when it does get published, and everything that sort of evolves after that can be captured in a different way. So yeah, it's gone through one research group last call. We'd like to, by the end of this presentation and then on the list, very soon move to another last call. So that's my goal here. We're now on the 5th version since the research group adopted it, and the changes that we've made most recently have been to scale back the section on self-censorship to the bare minimum there. Talked a bit more about domain seizure, again, like not under the sort of technical table of contents, which I'll get to in a second. And then we now also talk about how TLS 1.3 extensions are sometimes being blocked. That's, again, an example of how the longer we wait, the more new and novel ways to block the internet arise. So the table of contents, the summary of the draft, it's in essentially 4 parts. There's a section that sort of helps to define what to block. Then that's followed by a section on how to detect what to block after you've defined it. And then the last part is really about the actions that you can take to block it. And then there's some discussion of how the network is layered and how that actually matches. Yeah, I just saw Alyssa's point in the chat, which is absolutely right. We've talked a lot about how this could be a living document, but also how it might be useful to actually get it published once and then think about how to keep it up to date. So we are tracking this in GitHub. You can see the open issues. This is a just sort of list of what's open and my analysis of the way to move forward. So actually, since I submitted the most recent version, Ecker has given some really great suggestions to how to figure out issue 81 on the TLS identification piece. There's been an open issue for quite a while just to sort of incorporate, I think, this very relevant report. Thanks to Chris Wood for pointing that one out. There has been some treatment on issue 64 about the issue around TLS. And it's just that the original, the person who opened the issue, Chelsea, needs to review kind of the change we did and whether or not she's satisfied with that. There are 2 other issues that are still open, and I would actually, I'm coming here to you to recommend that we drop them. One is to introduce this concept of censor maturity, because again, I think this is something that maybe changes over time. I'm not sure it adds a great deal, and I also am just not very sure or clear what the text on censor maturity should be, since there's not been a suggestion. And then the other one I suggest dropping is changing. So throughout the document, we have a sort of trade-offs caveat under most subsections, meaning that, there's a cost to the censorship of some degree. And there's just been a suggestion that we change that terminology from trade-off to cost to implement, but I'm actually looking at the text. I don't think that the terminology change is really warranted, and also it would require us to do more wordsmithing, because then we tend to say trade-off : the cost to implement this, so it would be really redundant and kind of yeah, I'm just not convinced that it's really worth making the change. So anyway, so like I said, we're waiting for the re-review on issue 64. We know that we need to incorporate 81, 55, and 64 into the next version, and then we'll go to the list right after that's done, and hopefully ask the chairs for another last call. But wanted to stop there, I think, to ask if there were any questions or comments. Thanks again for the time. We have like 3 minutes left, I think.
Thanks, Mallory. Are there any questions from the meeting today? Otherwise, I think I can just say from the chair point of view, we're very keen to see this version move forward now that there's been some action on it again. So we would be very keen to have a discussion about setting a provisional date for getting to the next research group last call, so that we have some time-based targets to move this forward, because as you say, it really needs to be published at this point in time. So perhaps we can chat about offline when you think that might be reasonable.
I think it should be fairly imminent. Really, it's just, I feel really confident that the changes I need to make, I can make. It's just, I need the reviewers who originally raised them to just give me their stamp of approval, because I want to get it right. And I would just also say, I forgot to sort of say this in the presentation, and maybe it's only tangentially relevant, but there's also a brand new 00 draft that's going to be presented, I think, 3 times at IETF113 on IP blocking. This is, I think, reading between the lines in response to some of the requests that have been made of various internet infrastructure to action Russia's behavior during its war on Ukraine. And it's a good draft if folks want to read it. I think there's some overlap here. There's definitely some stuff in the IP blocking space that isn't in this draft. So I don't want to open that whole can of worms. I just want people to be aware of it and to note, that this draft has been around for quite a while. There's been a lot of really great thinking put into it, and I just like to see it get some attention.
Yeah.
So, yeah.
And if there are particular reviewers that you want feedback from, please let the chairs know so we can help you with that.
Cool.
And if you think those other drafts are useful for people from PEARG to provide input on, then please send that to the PEARG list so folks are aware of it. That would be great.
I did recommend that the authors send it to the list, the PEARG list. So we'll see if they will or not. So anyway, thanks all.
Perfect. Thank you very much for that. With that, I think we are wrapped up for today. Thank you to all our presenters today. And please continue to enjoy the hybrid IETF, whether you are remote or in person. Thank you very much, everyone.
Thanks all.